Quadratic equations. Let's start off by determining the x-intercepts of y equals 2 x minus 3 quantity squared minus 8. Okay, so remember the methodology is to set y equal to 0. So 0 is 2. X minus 3 squared minus 8. Add 8 to both sides. 2x minus 3 squared. Divide by 2. 4 is equal to x minus 3 squared. Square root, this will be plus or minus 2 is x minus 3. So x is equal to, move that over, 3 plus or minus 2. That gives us two answers. X is equal to 3 plus 2, which is 5. X is equal to 3 minus 2, which is 1. Okay, so the x-intercepts, x is equal to 1 and 5. I'm not putting parentheses around this. It's not ordered pairs. It's just a list of x-intercepts. Verify your answers by substitution. I'm going to talk you through this. 1 minus 3 is negative 2. Squared is 4 times 2 is 8. Minus 8 is 0. So the y value is 0. 5 minus 3 is 2. Squared is 4 times 2 is 8. Minus 8 is 0. So that's verification by substitution. You would substitute in the first value of x, evaluate, substitute the second value of x, and evaluate. Okay, you now need to read through the information down here. Here and say we're going to find x-intercepts of a graph, which are the x-coordinates of a point where the graph intersects the x-axis. Those are also known as the zeros of a function. They're the value of x that makes the function equal to 0, right? Y equals 0. What happens then? X-intercepts. And they are the roots of an equation. Roots of an equation are the solutions to the equation. So we can state this in three different ways, all of which basically mean the same thing, but one of which we're talking about a graph, one of which we're talking about a function, and one of which we are talking about an equation. So a graph, a function, which we've just done, right? That whole unit we did previously, y equals, that's the function, and an equation where it is actually set equal to 0. This discusses the roots. We already know about this, how a graph can open up and have a q value also up, which gives us no x-intercept. Also would work if it were down. So if a were negative and q were negative. One x-intercept or one real root, that happens when q is 0. And two x-intercepts, two real roots, when a and q are opposite signs. Right? But now we're really dealing with this, ax squared plus bx plus c. So we're going to solve equations, graphing it, finding the x-intercepts, factoring that and using the 0 property, which we'll get to, and completing the square and using the square root principle, and using the quadratic formula, which will be introduced later. Next worksheet, solving a quadratic equation by graphing the corresponding quadratic function. Since the roots of the quadratic equation, ax squared plus bx plus c equals 0, are the same as the x-intercepts of the corresponding quadratic function, y equals ax squared plus bx plus c. Okay, so in a function, it's going to be a y equals, or sometimes we'll see it as f of x equals instead of y. We can solve the equation ax squared plus bx plus c equals 0 by graphing the corresponding function and finding the x-intercepts of the graph. Okay, solve by graphing. Round answers to the nearest hundredth where necessary. So it won't always solve, so let's go to solve by graphing. I'm going to do this in Desmos. 3x squared minus 8x plus 5. Okay, here's the graph. Y equals 3x squared minus 8x plus 5. Here are my x-intercepts. If I hover over them, we'll see the coordinates. This one is at 1, 0, and this one is 1.667, 0. If we're rounding, then we can find these. And how would we find these on our graphing calculator? Well, one moment, and I'll pull up the graphing calculator. We'll look at it on there. Whoops, just disappeared the calculator. Okay, here's our calculator. We're going to enter y1 equals 3x squared minus 8x plus 5. Let's hit graph. That was table. Okay, let's hit graph. It's going to draw the graph. Now I can't really see my x-intercepts that well, so let's zoom in. We can see that we don't really need a lot of negatives, and we really don't need to go that far on our x's. So instead of zoom, I'm going to set my window. And let's say we go from maybe minus 5 to 5 with a scale of 1, and our y min, let's go negative 2 to 10, also by 1s. That'll bring us in a little bit closer. Okay, again, I've got two x-intercepts here. Let's find them. I like to do it this way, so I'm going to go to y equals, go down to y2 is equal to 0. Go back to the graph, and let's do an intercept. So second calc, second function, into the calc menu, number 5 is intersect. Whoops. Okay, one more time. Second calc, intersect, first curve. So I want to do an intersect, so I move down to about the point of intersection, right about there, and then I just hit enter 3 times. You'll notice the first curve, y1, that's my curve, 3x squared minus 8x plus 5. Second curve is y2 equals 0, and my guess is about there, and I can see the intersection, the x value is 1. And when we solve, we're looking for the x value. Okay, let's find the other one. Second calc, intersect, first curve. Now this time I'm going to move over. So you can see the cursor moving over. Hit enter 3 times. First curve, second curve, guess. And we get 1.67. Okay, so going over here, solve by graphing. X is equal to 1. X is equal to 1.67. Okay, to the nearest hundredth. 2x squared equals 9x plus 4. 2x squared, let's rearrange this, minus 9x minus 4 is equal to 0. I can graph this quadratic function, 2x squared minus 9x minus 4. I'm just going to bring up the calculator. Again, we'll do this off the calculator. Let's slide it over a bit. Okay, let's change our y equals, so it's going to be 2x squared minus 9x, so I can just edit this here, minus 9x minus 4 minus 4. Let's graph that, see what it looks like. Remember, I zoomed the window in, so okay, I'm going to go back. I'm going to hit zoom and then number 6 for standard zoom. Okay, and I'm interested in these two guys here. And since I've set y2 equal to 0, I'm just going to find the intersect. So second calc, number 5 is intersect. Let's move about to the point of intersection. It's a little past, and hit enter 3 times. First curve will be this, y1. Second curve, y2 equals 0. And my guess, again, I'm close. So we have negative 0.41, rounding to the nearest hundredth. Negative 0.41. And while we're here, let's do the other one. So second calc, intersect. Now I want to move over to here. If I follow y1, I'm going to have to go all the way down and then back up again. If I use my up or down arrow key, note how I now move to y2. And so right arrow means I'm just moving along the line y equals 0. Okay. First curve, in this case it can be y2. I only have 2 curves. Second curve, it jumps to the other curve, in this case the 2x squared. And my guess, about there. So we have 4.91. So my numbers are 0.41 and 4.91. Let's go write that in. X equals 0.41 and 4.91. So that's our two solutions. Okay, and of course that was negative 0.41 and 4.91. Those are two x-intercepts found by graphing. Okay, let's take a look at example 2. Path of a golf ball can be modeled by the function h of d. So in this case, function notation, height as a function of distance, horizontal distance, equal to negative 0.002 d squared plus 0.4 d, where h is the height in feet. It's actually really, and d is the horizontal distance traveled in feet. What is the maximum height reached by the ball? So we're going to do this by graphing. I'm going to come down and get the graphing calculator. Let's slide it over a bit. And let's graph this. So, hang on, I'm going to move stuff around a bit. Negative 0.002 x squared plus 0.4 x. Okay, let's just hit graph, see what happens. Now, it almost looks like a straight line, but that's the window we're looking at, right? And we're trying to model the path of a golf ball. So let's reset the window. I'm not interested in any negative portion of the graph. So I can go from 0. Now, how far might the golf ball go? It's traveling in feet. Let's try 300 feet. We'll try a 100-yard drive. And I'm going to want a scale of, let's say 50s. And how high? Well, again, we're not interested in negative heights, so let's go 0. I don't know how high, let's say 50 feet by 5s. And let's take a look at the graph and see how close we got. All right, and we're good. I mean, I can use this. Maximum height reached by the ball. Second function, calc. Number 4 is maximum. Left bound. So we want to stay on here, move over to the left. So I need to be left of the maximum. Hit enter. Right bound. Let's hold down the trace key. Trace over to the right of the maximum. And it needs a guess. So we'll go up to the middle. And you notice here we've got arrows showing where our boundaries are. So we're looking in between these two. And we hit enter. And the maximum height reached by the ball is 100. Ignore the 0.002. Okay, so 100 feet. 100. Okay, and we need units on here, right? Because it doesn't state it. It just says what's the maximum height. So we have to put the units on. If it had said what is the maximum height in feet reached by the ball, we wouldn't have needed these units. Okay, but here we do. What's the horizontal distance of the ball from the golfer when the ball reaches its maximum height? Okay, actually I think we had that. Look, wrong. The maximum height is 20, and that happened when the ball had traveled 100 feet. Let's go back and fix that. So the height, which is the y value, so remember we're writing this as y is equal to negative 0.002 x squared plus 0.4 x, so 20 feet. And that happened when the ball had traveled a horizontal distance, because our h is the y value and our d is the x value, horizontal distance of 100 feet, right? Let's go back here. Notice the maximum occurs at the point 100, 20, that's 100 feet for the d value, and the y value being the h is 20 feet high. What distance does the ball travel horizontally until it first hits the ground? So that's over here. When does it hit the ground? So we're looking for a 0. Now, we kind of know this by symmetry. If it reaches the maximum height at 100 feet, it will hit the ground at 200 feet, right? Traveled from 0, reached its maximum at 100. But using the calculator, second calc, I want a 0 value. And left bound, so we're going to head down towards that because our height will be 0. This, as long as the y value is positive, that will be to the left. Hit enter. Right bound, I need the y value to go negative, so it's done that. So I can hit enter. And a guess, I'm going to watch for the y value to get close to 0. That's close. Hit enter. And there we are at exactly 200 feet. Okay, so we did this using the graphing calculator, but we could equally have done it using symmetry. If it reached a maximum at 100 feet, then it would have to travel back down and hit at 200 feet. So 200 feet. Okay, And if we want, let's include a little sketch just to show what's going on. Okay, this is 200, this is 0, this is 100, this is 20, there's 10, there's all our points. Here's our point of interest, the vertex, which would occur at 100, comma 20, 120. And this is the point 200, 0 when it hits the ground. Next example. Manager of a store is investigating the effect that raising or lowering dress prices has on the daily revenues from dress sales. The function r at x is a revenue function. Now we've generated these in the last unit. Gives the store's change in revenue r in dollars from dress sales, where x is the price change in dollars. Determine the price change that will result in no change in revenue. Okay, so we want no change in revenue. Okay, so I've taken the liberty of bringing up the calculator and entering, albeit somewhat incorrectly because I have 2 squareds on there. So let's take that off. There we go. The function negative x squared plus 15x plus 100. Now what's the change in revenue is r, or in our case y. I've rewritten it to lead with the x squared term. When I graph this, what's no change in revenue? That will be in a y value of 0. So let's take a look at the graph. Goes up. Now we can see we have some negative here. Do we want a negative x value? Yeah, because we could, let's take a look, what's x? Where x is the price change in dollars. We could have a negative price change and also a positive. This is on a standard zoom, so I think I need to, I've got the curve coming up here. This is 1, 2, 3, 4, 5. I need to extend this out, and I need to extend this way up a bit. So let's change our window. We'll go from negative 10 is fine. Let's head out here a little bit further. So negative 10. Let's say we go to 25. Change in revenue, I'm going to go like minus 2 just so we can allow it to go down. And let's try 100. And all I'm doing is seeing if I can see the curve in here. So there it is. I don't have my maximum on here, so if I want to do that, let's go to Window and let's increase the Y max. Let's try 200 and graph that. And there we go. So this is pretty nice. I can see the whole curve here. What results in no change in revenue will be a Y value of 0, right? A revenue change of 0. So let's second calc. Now remember, since I have y2 still set to 0, I'm just going to do intersects. First curve, I'm just going to trace along until my y value comes down pretty close to 0. That's close enough. And I'm going to hit enter 3 times. First curve, second curve is 0, and third, and my guess. So we have negative 5 for x, so negative 5. That means if I lower the price by $5, I will not have a change in revenue. What I really want to do is get this point, right, the maximum. I want to find out what will give me my maximum revenue, but that's not really part of the question. So secondly, if I lower the price by $5, or second calc, number 5 is intersect. Now again, I'm going to jump down to y2 and I'm just going to move along this curve. And I'm looking to get out to the right hand side. We can just see the cursor coming through under the y is 0. And there it is. Close, close. Here we are. And hit enter 3 times. 1, 2, 3. And if I raise the price by $20, so determine the price change that will result in no change in revenue. This would be, I don't know how that snuck in. X is negative 5. Or x is 20, so a $5 decrease, $5 decrease, or a $20, I guess we can use a dollar sign, $20 increase. In both of those cases, we will have no change in revenue. All right, and just to kind of draw the graph, we see that it looks like this, and this was -5, and this was 20. If we wanted to maximize our revenue, of course, we would be looking for the vertex, right, which is not part of this example.